Alright, so we're continuing looking at induction proofs. So last week we got the idea of what induction is. We talked about the dominoes falling down, and that's kind of how this induction process works. And we talked about the different steps you have. So you have a base case, you have the induction stuff, which is an inductive hypothesis, an inductive step, and then you do a conclusion. We did a few proofs last week, which were about mostly summation things. So it was like prove that the sum of a certain set of numbers gets to this formula that you can use to calculate that sum. We're going to do two more types of induction proofs. So when I say types, what I mean is like the process is the same, but the thing we're trying to prove is something different. So in that first set, it was proving sums equal a certain formula. Now we're going to prove inequalities, and then we'll do something else with factoring. So, for example, we'll look at the statement. It says, prove that n is less than 2 raised to the n for all positive integers n. So what is that saying? That's saying that if I pick a positive integer, for example, 2, it should be less than 2 squared, which, yeah, it is. 2 squared is 4. If I pick 1, 1 should be less than 2 to the 1. Yep. Right, if I pick 5, 5 should be less than 2 to the 5. Yep. So testing out a few cases, we can see this kind of makes sense. So now let's try writing this proof. So base case is pretty simple. Well, first let's write what we're trying to prove. Trying to prove that n is less than 2 to the n for positive integers. Remember this notation as well. You can use this. So if n is a positive integer, n is less than 2 raised to the n. We can do a base case. That's basically the same kind of thing as we did in the previous proofs. So for n equals 1, well, 1 is less than 2 to the 1. Right? Because 2 to the 1 equals 2, 1 is less than that. This is like a mathematical sentence. You can write things this way. You can put an equal sign here. The equal sign just relates these two terms, and you're saying that 1 is less than everything to the right of it. So you'll see this sort of notation written a lot. So then we go to our inductive step, inductive hypothesis. So we're going to have to suppose something. So we're going to say, supposing we have n equals k, right, then we're going to say that k is less than 2 to the k. And then we move on to an inductive step. And so now we need to show, using that assumption, using what we supposed, we need to show that for k plus 1 is less than 2 to the k plus 1. So a proof like this, we're going to have to play around with a little bit differently. So let's take the statement that we suppose. So here we're going to start off with that assumption. We know from our assumption that k is less than 2 to the k. So I need to start making this look like this. Well, on the left side I have a plus 1, which I don't have over here. So I could add 1. I could do something like this, but I'd have to do it on this side as well. Or I'd have to do something on the right side. We don't know which one right now. Let's go with this first one. So if I add 1 to both sides, so I'm making the left side look the same. But then to compensate on the right side, I need to add a plus 1 as well. So now the left side looks the same, but the right side doesn't. But let's look at this. So for the right side, I need it to be 2 to the k plus 1. Right now my plus 1 is down here instead of up in the exponent. Well, 2 to the k plus 1, that's the same as 2 to the k times 2 to the 1. So I have the 2 to the k. Somehow I need to change this plus 1 to a times 2 to the 1. Well, I know that 2 raised to any power plus 1 is always less than 2 raised to something times 2. Or we can check that. If it was 2 raised to the 1 plus 1, that's 3. But 2 raised to the 1 times 2 is 4. Right? 2 squared plus 1, that's 5. But 2 squared times 2, that's 8. So that multiplying by 2, multiplying by a number bigger than 1, makes things bigger than just adding 1. And so that's using like some number sense logic. That's where these proofs kind of get tricky, is thinking about how can you get other things that are bigger to like continue the inequality. So if we know that this term, this expression, 2k plus 1, is less than 2 to the k times 2, and we know that k plus 1 is less than 2 to the k plus 1, then k plus 1 also has to be less than 2 to the k times 2. Using that transitive property, we know that A is less than B, B is less than C, so then A is also less than C. And then we can say that the 2 to the k times 2, that's the same as 2 to the k plus 1, all in the exponent. So finally we have k plus 1 is less than 2 to the k plus 1. So again, kind of a tricky thing in this math manipulation. That's where all these induction proofs kind of get a little tricky, right? We're trying to manipulate these inequalities or equations in ways that will help us get to what we want. And the guiding principle is to make this statement happen, right? So we want it to look like that statement. And so we're doing everything we can to rewrite things, getting there, sticking to math rules that we know. From the past, I know that this step is usually the thing that trips a lot of people up. And it's kind of something you get from practice, but really thinking about numbers and how they work, right? We're really, really, really looking at number sense on this. Thinking about like multiplication, that's going to be growing a lot faster than addition. In fact, like if I asked you, right, like does the line y equals, it's really what this is saying is like y equals 2 to the x, the line has a higher slope than x plus 1. Because like if you add 1, you're not changing the slope, you're just changing the y-intercept, you're changing the starting point, but it's just going up by 1 every time. Whereas when you multiply by 2, now you're also going up faster. That's kind of the unifying logic in all of this, right? That's why we talk about rates of change and derivatives and functions, except we don't have a direct function we're looking at here, but we're really just thinking about how these numbers work. Well, now we've shown the inductive step that it works for k plus 1. So then we can write a conclusion saying that therefore by induction n is less than 2 to the n for positive integers n. A lot of times when people write proofs, they do have a lot of work on the side like this, right? Playing around with it, trying to see what works. A lot of times you just have to do a lot of scratch work, try different things. When I write proofs like this, I always do a lot of test cases like this. It's not a full proof to do test cases, but doing examples like that can give you insights, can give you like patterns to see that then you can start generalizing into the variables that you have. So let's do one more like this. So this one we have, prove that n factorial is greater than 2 to the n for every integer n greater than or equal to 4. So to prove, we're showing that this inequality is true when n is bigger than or greater than 4 and it's an integer. So that's saying that 4 factorial should be bigger than 2 to the 4. Well, 4 factorial is 4 times 3 times 2 times 1. That's 24. And then 2 to the 4 is 16. Yep, that works. And then 5 factorial should be bigger than 32. And so that's 24 times 5, which is a very big number. It's greater than 32. And we can kind of see the factorials are going to get much bigger than the powers of 2 here. So starting off, base case. You got to be careful here. The base case is n equals 4 because that's the first thing that satisfies these conditions. N is an integer that's bigger than or equal to 4. So our base case is when n equals 4, not when n equals 1. I can show full factorial equals 24, which is bigger than 2 to the 4, which is 16. Then we do our inductive step. Our inductive hypothesis. We say, suppose for n equals k, k factorial is bigger than 2 to the k. For k bigger than 4. And then our inductive step would be then we need to show for n equals k plus 1 that k plus 1 factorial is bigger than 2 to the k plus 1. So now how do we show this? We're going to start off with the inequality we already have, k factorial bigger than 2 to the k. Just like we did last time, we start with the supposition inequality. And now we need to make it look like the thing in the inductive step. So on the left side, I need k factorial to turn into k plus 1 factorial. Well, k plus 1 factorial is really just k plus 1 times k minus 1, and so on. And k factorial is k times k minus 1, and so on. So this piece is the same on both those factorials. So the only new thing is multiplying by k plus 1. So let's multiply by k plus 1 on both sides. If I do that, now on the left side, I get k plus 1 factorial. And on the right side, I have 2 to the k times k plus 1. Now I need to show that I need to get it to be 2 to the k plus 1. So we're going to do the same trick as we did last time, where we know that 2 to the k plus 1 is the same as 2 to the k times 2. Well, here I have k plus 1, and here I have 2. And I need to show that this 2 is smaller than this, because then I can continue the inequality. Well, I know that k is always 4 or bigger, which means this number is always 5 or bigger, right? K plus 1 has to be bigger than or equal to 5, which means this whole expression is bigger than 2 to the k times 2. And so just like go through that again, make sure this logic makes sense in your head too as you're watching it and it seems clear to you. And if you aren't sure about something, if you're not exactly sure about it and it's not really like sitting well with you, try to like go through it again. You can ask me questions about it. We can talk about it during class time. And so now I have this full inequality. This equals 2 to the k plus 1. And so I've shown that k plus 1 factorial is bigger than 2 to the k plus 1. So I've done my inductive step, and now I write my conclusion. I can say, therefore, by induction, n factorial is bigger than 2 to the n for n greater than 4 when n is an integer. Induction proofs have weird logic in them sometimes. It takes some time to get your mind around it. Hopefully with this extra practice, and like this is the second week we're doing it, hopefully it's becoming clearer for you. So I'm going to end this video here, and then we'll do one more video with the other kind of proof I want to show you.